In this video, we're going to be taking a look at what's new with HoneyCrisp Emulator version 1.3.5. So to get things started off, I'd like to provide a listing of what's new with this version of the emulator and essentially go through each item on this list in order, just so you can get a better understanding of what I've improved and what I've changed with version 1.3.5. So what exactly is new? Well, there happen to be two primary additions, the first of which is a dual rendering system. Now later in the video, I'll go over what exactly this new rendering system is in a more in-depth manner. However, to give a quick rundown of what it is in a nutshell, is essentially the combination of the original terminal-based rendering system, which just takes text and puts it directly into a character grid on the emulated screen, and a new shader that I've developed, which uses WebGL technology to emulate the look of a CRT television. And so this dual rendering system essentially ensures that both of these rendering engines can coexist in the same environment, if you will, without bumping into one another. And so again, I'll go over what exactly this means for this version of the emulator and how this changes the overall code structure and how HoneyCrisp Emulator even renders its text onto the screen, but I'll save that for later in the video. The second primary addition pertains to bug fixes with how Integer Basic handles programs. Now, technically speaking, this is a smaller addition. However, it is one of the primary additions as it was a much needed one. For example, originally, an Apple I would have the ability to stop a running BASIC program with any key press. Well, prior to version 1.3.5, this was not possible due to the way I had the breakpoints for integer basic wired up into the keyboard, into the key buffer, that is. And so these bug fixes make it much more hardware accurate to how you would realistically stop a running basic program on an actual Apple I computer. And so this is likely what we're going to be focusing on first, as the CRT shader is a much larger, much more involved update that will take probably a much greater chunk of this video. And so with that out of the way, let's go ahead and move on to the demonstrations of both of these additions. We're going to first take a look at the bug fixes that have been made pertaining to how Integer Basic handles its programs, especially with stopping program execution. Now, as stated, this bug fix update to Integer Basic essentially makes it more hardware accurate in the sense of, instead of using explicitly the escape key or the key combination of Control-C, you can now press any key on the keyboard to stop a running BASIC program as long as it completes the current line that it is on. And so I'm going to go ahead and load up the program catalog so I can more properly demonstrate what this looks like. I'm going to go ahead and select 23 matches just as a simple example. And so as you can see, the program here is running just fine. However, if I continue running it and then get to a point where it is printing out, say, text for me to read or a prompt for me to interact with, I can press any key while it is actively performing that function to stop execution of the program. Editor Landon here. I should go ahead and mention real quick that the way integer basic interrupts programs can only be executed at the conclusion of a line. Therefore, the program, such as the one listed on screen now, cannot be interrupted. And this means that if a prompt is in the middle of receiving input from the user, even if it is printing the prompt, it cannot be interrupted while it is doing so. And so that said, let's just go ahead and move on with the video. I will be demonstrating the program listed in this little snippet from the manual here in a second to show you that programs such as that one cannot be interrupted. Anyway, enjoy the rest of the video. So, for example, I'll let this print out a little bit of the message and then press a key to show you what happens when I do so. So, I just pressed the J key on my keyboard, and as you can see, it successfully stopped the program from running at 300. And so, again, this is just a simple improvement that has been made. However, it is a much needed one, as it is certainly more hardware accurate than previous iterations were with how they handled stopping programs. So another improvement that has been made with integer basic is the ability to not stop specific programs as outlined in the preliminary Apple Basic manual. For example, if we were to clear Basic's memory by running a scratch command and then type the program as shown, outlined in the preliminary Apple Basic manual, and then run the program, as you can see, if we try to press any key to stop this program, it will not stop its execution. This also goes for trying to use the break button to stop program execution. It will not work. And the reasoning for this, as outlined in the preliminary Apple Basic manual, is because this line in particular never reaches the end of the line so it can move on from its initial execution. The reason it never moves on is due to this step 0 command here. This is basically telling the computer never move on from this initial for loop here. And so it will continuously keep running until you manually soft reset the computer to was1. And then from here, you could get back into the integer basic environment without losing your program by typing E2B3R, which will drop you back into the basic environment. And then if you list the program, you'll still have it in memory there. But this is just an example of one program that cannot be interrupted with any key press or with the break key. Now, this is clearly another improvement with version 1.3.5, as this sort of thing was completely incorrect in prior iterations of the HoneyCrisp emulator. And so with the integer basic stuff out of the way, I want to go ahead and take a moment to explain how the HoneyCrisp emulator renders text onto the screen, so I can prepare you guys for the explanation of the CRT shader in WebGL that I've developed. This is how the HoneyCrisp emulator renders text onto its emulated terminal screen. So as you can see here, the terminal is just 40 by 24 characters. It's just a perfect grid of ASCII2 characters. In the code, there is a second invisible grid, which is the same size as the first, that flags whether or not an @ symbol in the grid that is shown to the user was typed by the user or used internally by the system. This tracking system is essentially to make sure that an @ symbol that was rendered by the system blinks depending upon whether or not that at symbol is either the Wasmon cursor, the clear cursor, or the boot sequence at signs as you see here. So every time that you see a blinking at sign, the system is essentially checking whether or not that was typed by the user or it was used by the PROMs in the code itself. Every character gets checked before it lands on the character grid that is displayed to the user. Each character is stripped down to 7 bits, uppercased, and checked against the actual character set the Apple One supported. If any character typed is not in that set, it is effectively not displayed. This matches how the original Apple One's video circuitry performed. Now let's say that I type characters over and over again until I reach the bottom of the screen. As you can see here, certain rows are getting broken off because Wasmon only has a set limit to how many characters it can hold before it breaks off again and resets itself. And so now that we're at the last row, basically what the system does here is every time you enter a character, it is constantly performing a check to see if you have reached column 40 on the display. If you have, and you have effectively maxed out that column, like I'm about to do here, it will push every row behind it up by 1, mimicking the exact way a glass teletype functions, pushing each row up by 1, especially when you do a carriage return as well. Again, if I was to type 40 characters and then just keep going until I get to the bottom of the screen, it will automatically detect that I'm at the bottom of the screen and push everything up. And this will just keep happening until I clear the screen. If I clear the screen, it will put a cursor in the top left corner, the home position, and then allow me to start over. Here you'll notice that I'm typing a lot of text very, very quickly. Now you would usually think that something like this would cause the system renderer to essentially be called with every character that is outputted onto the terminal display. But in the case of if a user is pasting in large amounts of text like I currently am, essentially what happens here is the renderer is batching, again, it is batching text into strings and then outputting those strings of text that are being rapidly entered to the terminal display, so it doesn't have to constantly be refreshing itself every single time a new character is put onto the display. And this pretty much just helps with performance and lag on the display side of things. Again, if I'm to rapidly paste text, it is not refreshing itself with each character that is put onto the display. It is essentially outputting strings that it has essentially put together. And so again, this is just something that is very much needed for performance, as if it was called every single time a new character was put up onto the screen, that would slow things down immensely, and it wouldn't really match the original hardware. So going back to what we discussed earlier with the system essentially separating user-typed @signs from system-typed @signs, the cursor blink rate is separate from most of the main rendering logic. Um, it flips the @ sign cursor on a 350 millisecond timer, and that alone is enough to trigger a call from the main system renderer, even if nothing else on the screen changed. So it will re-render the screen if the cursor is actively blinking, which is pretty much always. Um, and so let's say that I have some text on the screen here. So I say I just output some uh, dummy text here, and I immediately clear the screen. You'll notice that the screen is instantly cleared. This is basically the rendering system clearing the entire visible screen, and it is effectively redrawing everything. However, it does it in one pass rather than piece by piece, which is why a scroll or a screen clear, as you just saw, shows up instantly instead of progressively drawing in. One last thing to mention would be that the rendering system does not recheck the entire screen every time that the rendering function is called. It only really tracks which rows have actively been changed. For example, if you type a character, move the cursor, and so on and so forth, only the rows that have actively been modified will be re-rendered. Everything else will stay the same. So every row, for example, below the cursor is exactly the same as it was before, and they have not been written over. And so this essentially makes it to where performance is improved even more so than it was prior, um, and reduces overall display lag. So with a more or less rough explanation of how the HoneyCrisp emulator handles rendering text onto its emulated terminal display, we're going to go to the settings and switch the display mode to CRT display. You'll notice that the screen warms back up with a slight curve and glow to it. Now I'm going to go ahead and full screen the terminal so you can see exactly what this looks like in a greater detail. Alright, so here we are in full screen on HoneyCrisp Emulator version 1.3.5, and we have the CRT mode activated, so you can see that we have a slightly curved tube-like appearance with scan lines and a phosphor emulation as well. A better example of how phosphor persistence is emulated here would be to clear the screen, for example. As you can see, it slowly fades out, and then there are copies of prior frames that are told to stay in view for just a bit longer so it can simulate a phosphor actually fading. And so we're going to enter a small machine code program into memory that will allow you to see just exactly how much better this is than your standard terminal display in terms of accuracy to the era, I suppose. And so if we do 0R, this will print out just a bunch of characters to the screen. And as you can see, it clearly has some phosphor ghosting trailing going on. And you'll especially notice it when the screen starts scrolling. Alright, so how exactly is this sort of shader effect achieved? Well, each frame that is executed, the terminal draws text to an off-screen canvas and gets fed into a WebGL system as a texture. It then blends the previous frame for phosphor persistence emulation, and then runs through a CRT shader pass for the scan lines and the bloom slash glow and the slight blur that is applied afterward. And so this is pretty much just how that works, and that's what's new with HoneyCrisp Emulator version 1.3.5. I hope you enjoyed this video, and if you did, please be sure to like it and subscribe. I would sincerely appreciate it.